So welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. So the first question, so a rigid closed tank contains 2 kg of an ideal gas. So you have a rigid closed tank. So it is the rigid closed tank. Contains a mass of 2 kg at a pressure. Maybe we can take it an initial pressure 500 kp. Maybe this is the initial mass amount 500 kp. Temperature 350 Kelvin. A valve is opened. So you have a valve. It is isolated through a valve. The valve is opened. Half of the mass of the gas is allowed to escape. That means this M finally becomes 1 kg. Because half of the mass is allowed to escape, then the pressure becomes 300 kPa. Mass becomes 1 kg. Pressure becomes 300 kPa. What is the temperature? T2. So because it is an ideal gas, so you can say that P2V volume is fixed. So volume is constant. So there is no change in the volume. So PV equal to MRT. So T2 equal to P2 V by MR. So this is M2. R is same for both because it is an ideal gas, so R will be the same. So P2 is known. So now we need V by R so that you can get from here. So this P1 V is same for both M1 R T1. So we want V by R, which will be equal to M1 T1 by P1. M1 is 2 kg, T1 is 350 Kelvin. P1 must be substituted in Newton per meter squared. So 500 into 10 power 3 Pascal. So this is 500 10 power 3 Pascal. Pascal is Newton per meter square. So that you get a proper unit. Okay, so that you can so it is 1.4 into 10 power minus 3. Maybe this unit will be in meter cube. By this will be joule per kilogram Kelvin. Okay, so this is what is that unit that you will get here. So now that if you substitute here, P2 is here, P2 also 300 10 power 3 Pascal, which is Newton per meter squared. P2 is M2 is 1 kg. V by R is already calculated. It is 1.4 10 power minus 3. (420 Kelvin). So answer is 420 Kelvin. Now we move to next question. So here at 400 kPa and 400 Kelvin and 200 kPa is heated at constant pressure. So that means it is a closed system. So when you say constant pressure heating process, that means it is a closed system. So you are heating it for a process 1 to 2. Definitely constant pressure heating means there will be a integral PdV work with the pressure constant process. So there will be a internal energy change U2 minus U1. So what is this internal energy change? So in kilojoule per kilogram mole. So we know that du equal to Cv dt. This will be in, if Cv is in kilojoule, kilomole, Kelvin, then dt is in Kelvin. So this product will be in kilojoule per kilomole. So now we can substitute Cv A plus Bt plus Ct squared into dt. Now this you integrate from 1 to 2. So you get internal energy change U2 minus U1 equal to AT plus Bt squared with 3, 1 to 2. So A, B, C, those constants are given that you can substitute, and the temperatures also. So the temperature from the initial temperature is 400 Kelvin. Initial pressure is 200 kPa to T2 is 600 Kelvin. So now you can U2 minus U1 is equal to A into T2 minus T1 plus B by 2 into T2 squared minus C by 3. So A is given 19.686, T2 minus T1, 600 minus 400 plus B by 2, 0.002 by 2 into 600 square minus 400 square plus C by 3, 0.5 into 10 power minus 5. So this much kilojoule per kilogram. Let's see what we are getting. So this will be 253.33. So the second part will be 200. So maybe the second part, this together, this is 200. So the answer will be 4390.53 kilojoule per kmol. So this is the answer. Rounded up to one decimal place. So 4.5. So now we move to question number 3. So a 5 kg metal block at 373 Kelvin is submerged into a 10 kg of water. So you have a water and a metal block. So this is the metal block. So this metal block has Cp, maybe CPM metal block. So we substitute in joule per kilogram Kelvin. Okay, since it is asked kilojoule per Kelvin, so we can take it kilojoule per kilogram Kelvin. Cp and the temperature, metal block initial temperature 373 Kelvin. Mass of the metal block. Mass of the metal block is 5 kg. This is about the metal block. So now this water, Cp of water 4.2 kilojoule per kilogram Kelvin. Temperature, initial temperature of water 293 Kelvin. Mass of the water 10 kg. So since the temperature of metal block is more than the water, so there is a heat transfer from the metal block to the water by which it reaches thermal equilibrium. So in the thermal equilibrium, this temperature changes to final temperature. Here this temperature changes to final temperature. These two final temperature will be the same because finally it will be at the equilibrium. So energy balance. So we can do energy balance first. energy lost by metal block equal to energy gained by water. Water at low temperature gaining energy. So that means mass of metal block, Cp of metal block into the initial temperature minus the final temperature. So maybe what we can take is this final temperature is the same as that of this final temperature. So those two temperature, because both metal block and water is going towards a final temperature which is same. So mass of water, Cp of water into the final temperature will be more here because water temperature is rising, metal block temperature is reducing. So the final temperature of water minus water initial temperature. So mass of water is 10, 4.2, sorry, mass of metal block 5.5, 373. This is the final temperature, 10, 4.2. See the final temperature minus 293. So you get the final temperature. So one step I write it here, 373 minus TF equal to 16.8 TF minus 4922.4. So the final temperature will be 297.5 Kelvin. Okay, so you got the final temperature. So now you go for the entropy change. So entropy change of the universe. So what we can do is we assume that this is the universe. So within the universe, you have a metal block and the water. So you can do the entropy change of the universe equal to entropy change of the metal block plus entropy change of the water. So the heat gained and lost is by a constant pressure. So there is no change in the pressure. So the heat is gained by the water and heat lost by the metal block is at constant pressure process. So this will be equal to mCp dt by T, dq by T. So we use dq by T for the entropy change. dq is the differential amount of heat lost by metal is mCp dt by T. Same thing for the water also. This is for metal block. Similarly, mCp dt by T for water. So you can take m metal block, Cp of metal block, ln the integration from initial to final. Same thing, initial to final. Final temperature to initial temperature of the metal block plus water, Cp of water, ln final temperature by final temperature in both the cases will be the same, initial temperature of the water. Now substitute all the values. Mass of the metal block 0.5, 5 kg, Cp is 0.5, 5 kg, 0.5. So since you are substituting this Cp in kilojoule per kilogram Kelvin, mass is in kilogram. So you will get kilojoule per Kelvin. So we want the answer in kilojoule per Kelvin. 373 is the initial temperature, 297.5 is the final temperature. Ln 297.5 by 373. 373 plus mass of water will be 10, 4.2 ln 297.5 by 293, 293, 293. So this will be your answer. This is minus 0.565 plus. See, entropy change of the universe will always be positive. So that you just keep it in mind. 297.5 0.64. Point 0.075 kilojoule per Kelvin. So this will be your answer. Okay, so maybe the nearest answer will be 0.073. So this will be your answer. So that is what you are getting nearest. So now we move to the next question. So a piston cylinder device initially contains 1 meter cube of air. So you have a piston cylinder device. So initial volume 1 meter cube at a pressure 200 kPa, temperature 25 degrees centigrade. Air expands at constant pressure. So it is expanding integral 1 to 2 pdv at pressure constant process. Maybe the process 1 to 2 is a pressure constant process. Well, a heater is at 250 watts. So you have a heater. So that is 250 watts. Switched for 10 minutes. So that means the energy given here through this 250 watts is 250 joule per second into 10 minutes. 10 into 60 second. So this much joule. But the answer what we want, okay, so we will put in joule itself. 250 into 10. So 150 joule. So the energy given in here through the heater is 150 kilojoule. And the energy which is going out by a heat loss in the process 1 to 2. So this is the energy which is given in by the heater. 150 is the energy in. So which we will take it E1. Energy in. Heat loss E1 to 2. Energy in during the process 1 to 2. Q1 to 2 is 4 kilojoule. Assuming air as an ideal gas, so what is the final temperature of the air? So initial temperature is this. What is the final temperature? So this is what we want to find out. So here we can apply the energy balance equation. Energy in minus energy out equal to change in energy of the system. Energy in is, maybe we will write in joule, 150 into 10 power 3 joule energy is going in. Then energy integral pdv is the energy out, expansion. So that is integral 1 to 2 pdv is equal to pressure is constant, will be V2 minus V1. Because it is an ideal gas, so you can write mR into T2 minus T1. Because it is an ideal gas. Assuming air as an ideal gas. So ideal gas. So ideal gas PV equal to mRT. So using this, we can write this integral PdV. So energy in, so there is an energy out, 4 kilojoule. 4 into 10 power 3 joule of energy is going out. And then this mR T2 minus T1. This energy is also the expansion work, which is going out. So, and then change in internal energy, mCV into the temperature change. This is an internal energy change. So this will be 146 into 10 power 3 is equal to m into r plus Cv T2 minus T1. So we know that Cp minus Cv equal to R. Cp is equal to R plus Cv. M Cp into T2 minus T1. So T2 minus T1 you can substitute in degree centigrade because it is a temperature difference. Cp is, so now you can substitute those values. It is in joule. Mass we need to calculate because you are given P1 V1 by R P1 is equal to your mass. So P1 is 200 into 10 power 3. V1 is 1 divided by, because this must be substituted in Newton per meter squared. 200 into 10 power 3 Pascal. Pascal is Newton per meter squared. R is 287 joule per kilogram Kelvin. Temperature must be in Kelvin. So 25 plus 273. So this will be 298 Kelvin. So mass. Two point 34 kg is the mass. So 2.34 into Cp is 1005. We want in joule per kilogram Kelvin. So this must be substituted in joule per kilogram Kelvin because the other side, the energy is in joule. Temperature difference. So T2 minus, if you substitute in degree centigrade, you will get the answer in degree centigrade. So 25. So you get 18 degree. If you substitute in Kelvin, you will get in Kelvin. Eighty-seven point one degree centigrade. Final temperature will be 87.1 degree centigrade. So that is the answer. Now we will go see the question number 5. Steam at 2 MPa and 300 degrees centigrade steadily enters a nozzle. So you have a nozzle. So this is section 1. This is section 2. So the inlet diameter 20 centimeter, 0.2 meter, because 100 centimeter is 1 meter. So 20 centimeter is 0.2 meter. Steam leaves the nozzle with a velocity. So V2, 300 meter per second. The mass flow rate of the steam through the nozzle 10 kg per second. So steady flow device. So mass flow rate is same at inlet and exit, 10 kg per second. Assume no work interaction and no change in potential energy. Heat loss from the nozzle. So there is a heat loss from the nozzle, which is 3 kilojoule per kg. 3 kilojoule per kg of steam. So exit enthalpy. So what is the exit enthalpy? In kilojoule per kg. This is what we want. Since velocity is there meter per second, you must substitute enthalpy in joule per kilogram. So you have here enthalpy and velocity V1. Now apply the steady flow energy equation. So enthalpy, kinetic energy, potential energy will be 0. So this is so maybe energy in equal to energy out. So this is your steady flow energy equation. So energy in is mass flow in with an enthalpy kinetic energy, potential energy neglected, which will be equal to enthalpy out kinetic energy, potential energy neglected, and then heat going out. So this is the, so heat is known, enthalpy at the inlet, it is given for 2 MB and 300. So this is the enthalpy at the inlet. So H1 is known. V2 is known. V1 we need to find out so that Q is known, so that we get to the H2. So how do we find out V1? So if we know that mass flow rate is equal to rho 1 A1 V1. So this will give you the velocity V1. Density you can find, this is the inlet. So density is equal to 1 by the specific volume. So 7.967 kg per meter cube. This is the density. So now mass flow rate is known. Density is 7.967. Area is pi by 4 d1 squared into v1. So we get the v1. So it is 39.95 meter per second. So we know the velocity. Now you can substitute. H1 must be in joule per kilogram because velocity is in meter per second. So 3024 200 joule per kilogram, because your velocity is in meter per second. When you substitute velocity meter per second, v squared by 2 is in joule per kilogram. So that is why the H1 must be in joule per kilogram. So this will be 39.9 squared. H2 is what we want. V2 is 300. Q must be in kilojoule per kilogram. 3000. Okay, so now H2 you get in joule per kilogram from this equation. Two nine 76 998 joule per kilogram. So we wanted it in kilojoule per kilogram. So 2976.998 kilojoule per kilogram. So this will be rounded off to nearest integer. Nearest integer is 2977 is the answer. Thank you for watching this video. If you are happy with this video, please subscribe the channel and share this to your friends who are preparing for GATE mechanical engineering subject. If you want to join for GATE 2026 video course, please contact in the number mentioned here.